Here's a sentence: she sat by the bank and watched the water go by. You knew instantly that this bank is the edge of a river, not a place that keeps your money. Nobody told you. You didn't look it up. You figured it out from the words around it, from the context. Now change one word. She sat by the bank and deposited her paycheck. Same 4 letters, completely different meaning, and again you resolved it without effort because the word deposited quietly reached over and reshaped what bank means. Notice the direction of that. The meaning didn't come from inside the word, it came from a neighbor. Language is full of this. Take the sentence, the animal didn't cross the street because it was too tired. What does it refer to? The animal, obviously, but swap tired for wide and suddenly it means the street. One word 8 words away flips the reference and you follow along effortlessly without ever noticing you did anything at all. And this is genuinely hard. That word, it has no meaning of its own worth speaking of. It is a pointer with nothing written on it. To understand it, you have to scan the sentence, weigh several candidates, and pick the one that fits, using a piece of information, tired, that sits at the very end. A machine that reads strictly left to right, one word at a time, is in real trouble here. This is the deep truth that all of modern AI is built on. The meaning of a word is not fixed. It depends on the other words it lives with. So the real question is, how could a machine ever learn to do what you just did, to let every word look around at its neighbors and update its own meaning? The answer is a mechanism called attention. Today we open it all the way up, right down to the equations, and by the end you'll understand every symbol in the single most important formula in modern AI. Let's begin. Chapter 2: The problem attention had to solve. Before we build the answer, it really helps to feel the problem, because for years the best language models in the world handled text in a way that had a deep structural weakness, not a bug you could patch. A weakness baked into the shape of the thing. The old approach: read a sentence the way you might read in the dark with a single candle. One word at a time, left to right, holding everything you'd seen so far in one small, running memory, a single vector of numbers called the hidden state. Read a word, update the memory, move on. These were called recurrent neural networks, and for a while they were the best we had. But think hard about that running memory. It is a fixed size. It does not grow when the sentence gets longer. By the time the model reaches the end of a long paragraph, the beginning has been squeezed and overwritten and squeezed again, faded almost to nothing. Connecting a word at the end to a word far back at the start meant passing information through every single step in between, and along that path it decayed. Researchers had a name for the gentle version of this, vanishing gradients, and a name for the whole shape of the problem, the long-range dependency problem. It got worse for translation. The standard design read the entire source sentence into one final vector and then generated the translation out of that single vector. One fixed-length summary carrying an entire sentence. People called it the bottleneck, and the results showed it. Translation quality held up on short sentences and fell off a cliff as they got longer, exactly as you'd expect when you keep pouring more water into the same small cup. And there was a second problem, just as serious and in the end more decisive. Because each word had to wait for the one before it to be processed, the whole thing was stubbornly sequential. Step 50 could not begin until step 49 had finished. You could not do it all at once. And this was happening right as the field was moving onto graphics hardware, which is essentially a machine for doing thousands of small things simultaneously. The models were built to walk, on hardware built to sprint in every direction at once. So the field had a wish list, and it was short. 1, a way for any word to reach any other word directly, no matter how far apart. 2, a way to do it for every word at the same time in parallel. Both of those wishes took years to grant. The first one arrived in 2014. Chapter 3: Where attention actually came from. This is a piece of history that gets told wrong constantly, so let's get it right, because the correct version makes the whole idea much easier to understand. In 2014, 3 years before the famous paper, Dimitri Bodanov, Kyung-hyun Cho, and Yoshua Bengio published work on machine translation with a simple, powerful diagnosis. The bottleneck is the problem. Forcing an entire source sentence through one fixed vector is the thing holding us back. So don't, instead, keep every word's hidden state from the source sentence, all of them, and let the decoder look back at all of them, every time it produces a word. But look back how, not equally, that would just be an average, and an average of a whole sentence tells you very little. Instead, at each step, the model computes a small set of weights, one per source word, saying how relevant each source word is right now. Then it takes a weighted blend. When it's about to translate the verb, the weights concentrate on the verb. When it's on the object, they slide over to the object. They called this a soft alignment, and it was learned, not programmed. Nobody wrote a rule saying French adjectives usually follow the noun. The model discovered where to look entirely from the data. And when the researchers drew those weights as a grid, you could literally see the alignment between the two languages appear as a bright diagonal ribbon. That picture of a model showing you where it's looking is one of the most influential images in the history of the field. A year later, in 2015, Minthang Liuang and colleagues at Stanford tidied it up. They compared ways of computing those relevance scores and found that a plain dot product between vectors worked beautifully and was far cheaper than the small neural network the original had used. Remember that, the dot product, because it is about to become the beating heart of everything. By 2016, attention exists, it works, and everybody uses it. But note carefully what it is at this point. It is an accessory. A helper bolted onto the side of a recurrent network, which is still doing the actual reading, still one word at a time, still sequential. Wish number 1, granted. Wish number 2, parallelism, still completely out of reach. Chapter 4, the idea that changed everything. In June of 2017, 8 researchers at Google published a paper with one of the boldest titles in the history of computer science. Attention is all you need. And the title is the whole argument. Everyone had attention as a helper. Their radical move was to ask, what if the helper is the entire thing? What if we take the recurrent network, the slow sequential machinery that everyone assumed was doing the real work, and simply delete it? The paper's own words are wonderfully blunt. They propose an architecture, quote, dispensing with recurrence and convolutions entirely. And one honest correction, because you'll hear this said wrong. This paper did not invent attention, as we've just seen, and it did not invent self-attention either, a word attending to other words in the same sentence, which had appeared in earlier work. What it did was put self-attention at the center and remove everything else, and then show that the result was not just competitive but better and dramatically faster to train. It popularized and proved the idea. That's a different and frankly larger achievement than inventing it. Here's that idea in one breath. Instead of passing meaning down a chain, word by word, let every word look directly at every other word all at once and pull in whatever it finds relevant. No chain, no waiting. Not a line of people whispering down a row, but a room where everyone can hear everyone simultaneously. The results made the case for them. On English to German translation, their model set a new state of the art, and it trained in a fraction of the compute the previous best models needed. Better results, less time. That combination is what makes a field change direction. That architecture is called the transformer, and it is the engine inside almost every large language model you have ever used. For the rest of this video, we are going to build its beating heart, attention, one piece at a time, with the real notation, until that formula from the paper feels not just clear, but inevitable. Chapter 5, Query, Key, and Value. This is the heart of the whole idea, so we'll take it slowly. Analogy first, then the actual math, then the actual dimensions from the paper. Imagine a word walks into a library and asks a question. I'm the word it, I'm looking for whatever I refer to. That question is called the query. Every other word in the sentence is like a book on a shelf, and each book has a small label on its spine describing what it offers. That label is called the key, and the actual content the book will hand over, if it's chosen, is called the value. So every single word at the same time produces 3 things: a query saying what am I looking for, a key saying what do I offer to others, and a value saying here is what I'll contribute if you attend to me. Query, key, value. Hold on to those 3 words, because absolutely everything else in this video is just how they interact. And you might reasonably ask, why 3? Why not just compare the word vectors to each other directly? Because the roles are genuinely different. What a word is looking for is not the same as what it advertises, which in turn is not the same as what it contributes. The word tired advertises itself as a property of a living thing, that's its key. But what it hands over, its value, is the actual semantic content, exhausted, needing rest. Splitting those apart gives the model three independent things to learn, instead of forcing one vector to do three jobs. So where do these three come from? Each one is just the word's own embedding vector, multiplied by a matrix that the model learned during training. Query equals the word times WQ, key, times WK, value, times WV, three different learned lenses on the same word. That's it. No magic, just three linear projections, and those three weight matrices are among the parameters that pre-training tunes. And the paper gives us exact numbers, so let's use them. In the base transformer, each word vector has 512 dimensions. That's called D-model. The queries and keys are projected down to 64 dimensions each, called DK, and the values also to 64, called DV. WQ is 512 by 64 matrix, and so are the other two. Real, concrete shapes, nothing abstract about it. So now every word in the sentence is holding up three things: a question, a label, and an offering. The next step is to let the questions meet the labels. Chapter 6, Scoring, or How Relevant Are You to Me? A query is a question, a key is a label. To find the right matches, we need one number that measures how well a given query fits a given key. The tool for that is the dot product, and it is beautifully simple. Take two vectors, multiply them element by element, add up the results. One number out, and that number has a clean geometric meaning. If the two vectors point in roughly the same direction, the products reinforce each other, and the total is large and positive. If they point in unrelated directions, the terms cancel and you get something near zero. If they point in opposite directions, you get a large negative number. So think of it as an alignment meter. During training, the model shapes the query matrix and the key matrix so that a word's query points in the same direction as the keys of the words it should care about. Learning what to pay attention to becomes, quite literally, learning which directions to point in. That is a lovely thing to sit with for a second, because it means attention is doing geometry, not lookup. Now do that for every query against every key. The word it asks its question of animal, of street, of tired, of every word in the sentence, and each pairing produces a score, and every other word is doing the same. Stack all of that up and you get a grid, a square table of every word's relevance to every other word. In the paper's notation, that entire grid is a single matrix multiplication, Q times K transpose. It's worth pausing on the shape of that. If your sentence has n words, Q is n rows by 64 columns, K transpose is 64 rows by n columns, so the product is n by n. One row per word, one column per word. And that n by n is the single most consequential fact about the transformer, because it means the cost grows with the square of the sentence length. Double the text, quadruple the work. We will come back to that, and it is the reason the next video exists. These raw scores are the model's first rough opinion about what matters to what, but they are unbounded, they can be enormous or wildly negative, and in that state they are unusable. Before we can act on them, we have to tame them. Chapter 7, The Square Root of DK. This is one line in the paper, tucked away in a footnote, and it is the detail people most often skip. We're not going to skip it, because understanding it tells you something real about how these models train. Here's the step itself. Before doing anything else with those raw scores, divide every one of them by the square root of DK, the square root of the key dimension. In the base model, DK is 64, so the square root is 8. Every score gets divided by 8. That's the whole operation. The interesting part is why. The paper's own footnote gives the argument, and it's a short piece of statistics. Suppose the entries of the query and key vectors behave like independent random numbers with mean 0 and variance 1. Their dot product is a sum of DK such products. Each product is variance 1, and when you add up DK independent things, the variances add. So the dot product has variance DK, and therefore a typical magnitude around the square root of DK. So put numbers on it. With DK equal to 64, raw scores naturally swing around plus or minus 8, and outliers go well past that. With a bigger key dimension, they'd swing wider still. The scale of the scores depends on a design choice that has nothing to do with meaning, which is exactly the kind of accident you want to correct for. divide by the square root of dk, and the typical score is back around 1, whatever dimension you chose. And why does that matter so much? Because of what happens next. Softmax, which is exponentially sensitive to the size of its inputs. Feed it scores spread over a range of 8, and it will effectively pick a single winner and crush everything else to nearly zero. The paper says this pushes softmax into regions where it has extremely small gradients, which is the technical way of saying the model stops being able to learn from it. The signal that says, actually, you should have looked slightly more at that other word, becomes too faint to act on. So a single division by 8 is the difference between a model that trains and a model that stalls. That's the kind of detail that separates an idea that works on paper from one that works at scale. Now let's meet the function it was protecting. Chapter 8, Softmax, or How to Spend a Fixed Budget of Attention. We have a row of scaled scores, one for each word in the sentence, and they're still just arbitrary numbers, some positive, some negative. We need weights. Softmax does two things. First, it exponentiates each score, which makes everything positive and stretches the gaps, so a slightly higher score becomes a noticeably higher weight. Then it divides each one by the total, which forces them to add up to exactly 1. Comes a set of numbers that are all positive and sum to 100%. So here's the picture I want you to carry. Every word gets exactly 100% of attention to spend, and not a drop more. Softmax is the accountant that decides how it's allocated. Maybe 80% goes to one word, 12 to another, and the rest is scattered as small change. Attention is a zero-sum competition. For one word to get more, another has to get less. Nothing in the mechanism enforces that except this single function, and it changes everything because it forces the model to actually choose. And it's called softmax for a reason. A hard max would pick the single best word and give it everything. Softmax gives you a smooth, differentiable version of picking a winner, one that can also say, honestly, these 3 words all matter somewhat. That smoothness is what lets gradients flow back through it during training, and it's why we can learn attention at all rather than having to hand design it. So now each word holds a tidy row of weights, a considered, quantified opinion about exactly how much to listen to every other word in the sentence. All that remains is to act on it. Chapter 9, the weighted sum, where the whole thing comes together. We have the attention weights. Now, finally, we use the values, the actual content each word offered up. The step is simple. Take a weighted sum of the value vectors, using the attention weights. If the word it is paying 80% of its attention to animal, then 80% of animal's value vector flows into the result with smaller trickles from everything else. Add them all up and you get one new vector, 64 dimensions in the base model, which is the output for the word it. And I want to be precise about what just happened because it's the whole point. That output is a brand new version of the word it, not the generic pronoun it started as, but a version that now carries the meaning of animal mixed right into it. The word has been rewritten by its context. Do this in one layer, then feed the result into another layer that does it again and again, 6 times in the base model, and words progressively absorb more and more of the sentence around them. That is how a machine reads meaning in context. And that is the entire mechanism. Every piece we've built clicks into a single line, the one from the paper. Attention of Q, K and V equals softmax of Q times K transpose, divided by the square root of dk, all times V. Read it right to left and it's the story we just told. Q times K transpose gives scores, divide by the square root of dk so softmax stays gentle. Softmax turns scores into a budget, multiply by V to blend the content. You now understand every symbol in the most important formula in modern AI. Formulas are one thing, numbers are another. Let's do it by hand. Chapter 10, a worked example small enough to do in your head. Let's shrink everything down. 3 words and vectors of just 2 numbers instead of 512, so we can actually watch the arithmetic. Our 3 words are animal, street, and it. After their query key and value projections, suppose the query for it comes out as 1.0, 0.5. The key for animal is 1.0, 1.0. The key for street is 0.1 minus 0.8. And the key for it itself is 0.2, 0.1. Now the dot products, query for it against key for animal 1 times 1 plus 0.5 times 1 equals 1.5. Against street 1 times 0.1 plus 0.5 times minus 0.8 equals minus 0.3. And against itself 0.2 plus 0.05 equals 0.25. So already, before any training-specific magic, animal is far and away the best match. The geometry did that. Now scale our dk here is 2, so we divide by the square root of 2 about 1.41. 1.5 becomes 1.06, minus 0.3 becomes minus 0.21, and 0.25 becomes 0.18. Notice the ordering is untouched. Scaling never changes who wins, it only changes how sharply the winner is favored. Now softmax across those three, exponentiate. E to the 1.06 is about 2.89, e to the minus 0.21 is about 0.81, e to the 0.18 is about 1.2, they total about 4.9. Divide each by that total and we get roughly 59% on animal, 16% on street, and 25% on it itself. There's the budget fully spent. Finally, the weighted sum. Take 59% of animal's value vector, plus 16% of streets, plus 25% of its own, and add them. Out comes a single new vector for the word it, dominated by animal but not purely animal. And that is one pass of attention, complete, in numbers you could check on paper. The real thing does exactly this, with 512 dimensions, thousands of words and billions of these operations per second. The arithmetic does not get harder, it only gets bigger. Chapter 11, seeing it in a real model. Let's bring back our sentence. The animal didn't cross the street because it was too tired. This exact example appears in the paper's own appendix, where the authors visualized what their heads had learned. Here's the attention grid, every word along the top, every word down the side, each cell shaded by how much attention flows from the row word to the column word. Most of the grid is quiet, pale, unremarkable, but find the row for the word it and follow it across. One cell is bright, almost glowing. It's the cell connecting it to animal. That is the whole idea made visible. The model, entirely on its own, learned that to understand the word it, you look at animal. Nobody wrote a rule for pronoun resolution. Nobody labeled a single example of it. The pattern emerged from training on enough language that the geometry settled into place. And if we had written too wide instead of too tired, that bright cell would slide over to street all by itself. Nothing else worth naming here. Almost nothing inside a neural network is interpretable. You get billions of numbers with no obvious meaning. Attention weights are the rare exception. They're a picture of what the model looked at in a form a human can read. That has made attention maps one of the main windows we have into these systems, and it's a real part of why the mechanism caught on so fast. Though a fair caveat, researchers have since shown that what a model attends to isn't always the same as what it relies on. The picture is informative, not a full explanation. That one glowing cell is the aha of this entire field. Now let's pull back and watch it happen for every word at once. Chapter 12, Self-Attention all at once. We followed one word it as it searched the sentence. But here's the part that makes the whole thing fast. Every word is doing exactly the same thing, at exactly the same time, and none of them wait for each other. Animal is looking around, street is looking around, the word the is looking around. Every word issues its query, checks it against every key, and blends the values it cares about, all simultaneously. This is called self-attention because the sentence is attending to itself. Same sequence in all three roles, queries, keys, and values. And the reason it can all happen at once is that it's not a loop, it's a matrix multiplication. Stack every word's query as a row and you have the matrix Q, same for K and V. Then Q times K transpose computes all the scores in one operation, softmax runs across each row independently, and the multiply by V produces every output in one more operation. 3 big matrix multiplications for an entire sentence. Graphics processors are essentially machines built to do exactly that. So look at what we've achieved. Remember the wish list from Chapter 2. Any two words connected directly, no matter how far apart, granted, because attention connects word 1 to word 500 in a single step, with no decay in between. And every word processed in parallel, granted, because the whole thing is matrix multiplication. The bottleneck is gone, both wishes at once. We now have a mechanism that lets an entire sentence rewrite itself in context, in one shot, but there's a way to make it dramatically richer, and the paper takes it. Chapter 13, Multi-head attention. There's a real limit to what we've built so far, and once you see it, you can't unsee it. A single attention pattern gives each word one row of weights, one budget, one opinion about what matters, but language does not have one relationship at a time. In a single sentence, you might need to track which pronoun refers to which noun, and which adjective modifies which noun, and what the subject of the verb is, and which clause a phrase belongs to all at once. If a word only has 100% of attention to spend, and it spends it all on resolving a pronoun, it has nothing left for grammar. One grid simply cannot represent all of that. The paper's answer is wonderfully direct. Don't run attention once. It's several times in parallel, each copy with its own learned query, key and value matrices. Each copy is called a head. Each one gets its own full budget, its own lens on the sentence. The base model uses 8 heads. And here's the elegant part, the dimensions. You might expect 8 heads to cost 8 times as much. They don't. The model dimension is 512, and instead of giving each head all 512, the paper gives each head 64, because 512 divided by 8 is 64, so dk equals d model over h. 8 heads of 64 cost almost exactly the same as 1 head of 512. You get 8 perspectives for the price of 1. The paper says this outright. The total computational cost is similar to that of single head attention with full dimensionality. Then the results are recombined. Each head produces a 64-dimensional output per word. Concatenate the 8 of them back into 512, then multiply by one more learned matrix, WO, which lets the model blend and weigh what the different heads found. Concatenate, then project. That's multi-head attention complete. And what do the heads actually learn? Nothing is assigned. But when researchers look inside trained models, they find heads that specialize remarkably cleanly. Some track syntactic dependencies, some follow pronouns, some just look at the immediately preceding word. Some appear to do very little at all and can be pruned away with barely any loss, which is its own interesting finding. The division of labor is emergent, not designed. Multi-head attention is a large part of why these models feel so linguistically sharp, but there's a strange gap in everything we've built so far, and you may not have noticed it yet. Chapter 14, the same mechanism in 3 different jobs. So far we've talked about attention as one thing. In the original transformer it's used in 3 distinct ways, and the difference between them is purely a question of where the queries, keys, and values come from. First, encoder self-attention. The encoder's job is to read and understand the input. Here queries, keys, and values all come from the same place, the previous encoder layer, and every word may look at every other word, both directions, no restrictions. Full, unrestricted understanding of the input. Second, decoder self-attention. The decoder's job is to write the output, one word at a time. Again, all 3 come from the same place, but with one crucial restriction: a word may only attend to words before it. We'll spend a whole chapter on that shortly, because it's what makes generation possible at all. Third, and this is the interesting one, cross-attention. Here the queries come from the decoder, but the keys and values come from encoder, so the sentence being written asks questions of the sentence being read. This is the direct descendant of Bodenau's 2014 idea, the same soft alignment, now expressed in the same clean query, key, value language as everything else. One mechanism, 3 configurations. And a note on today because it matters for the rest of this series. The models people actually use now, the GPT family and its relatives, are decoder only. No encoder, no cross-attention, just a tall stack of masked self-attention. Prompt and the response are all one sequence, and the model simply continues it. The full encoder-decoder shape lives on mainly in translation and a few specialized systems. One mechanism, wired 3 ways now, that gap I mentioned. Chapter 15, the problem of order. Here's the gap. Look one more time at how attention works. Every word compares itself to every other word in one big simultaneous pile of dot products. Nothing anywhere in that machinery knows which word came first. Think about what that actually means. To attention as we've built it, the sentence "the dog chased the cat" is identical to "the cat chased the dog." Exactly the same set of words, exactly the same set of pairwise comparisons, exactly the same output, just shuffled. The technical term is permutation equivariant, and for language it is a catastrophe, because word order carries an enormous amount of meaning. The very thing that made attention fast, throwing away the sequential chain, also threw away the sequence. So the paper puts the information back in directly. Before words ever enter the first attention layer, each one gets a positional encoding added to its embedding, a distinct pattern of numbers that encodes where it sits in the sequence. First position, second position, third. Same word, different position, different vector going in. Note that it's added, not attached alongside. Position and meaning share the same 512 numbers. And the choice of pattern is genuinely clever. The paper builds it from sine and cosine waves at many different frequencies. Fast oscillating dimensions distinguish neighboring positions. Slow ones capture broad location in the sequence. It's essentially a binary clock written in smooth curves. And they chose it for a specific reason, which they state in the paper, that for any fixed offset, the encoding of a position a few steps later can be expressed as a simple linear function of the current one, which means relative distance is something the model can learn to read off easily. It also has a practical benefit. Because it's a formula and not a lookup table, it produces a valid encoding for any position, including positions longer than anything in the training data. The paper hoped this would let models extrapolate to longer sequences. In practice, that hope was only partly met, and finding better ways to encode position became one of the most active research threads of the following decade, which is a story for the next video. With position stitched in, attention finally knows not just who is talking to whom, but in what order. One essential piece remains, the one that turns understanding into writing. Chapter 16, The Causal Mask, or No Peeking at the Future. A model that writes text does it one word at a time, predicting each next word from everything that came before, and that creates a strict rule during training. Here's the situation. To train efficiently, we show the model an entire sentence at once and ask it to predict the next word at every single position simultaneously. That's enormously faster than one position at a time, but it creates an obvious cheat. When predicting the word at position 5, the full sentence is sitting right there, including position 6, which is the answer. A model that can see the answer will learn to copy it and learn nothing whatsoever about how to generate. The fix is elegant. Take the attention grid and block out the upper triangle, every cell where a word would be looking forward in time. Set those scores to negative infinity before the softmax, then exponentiate. E to the minus infinity is 0. So after softmax, those cells are exactly 0, not merely small, and the remaining weights still sum neatly to 100% across the words that are allowed. No attention leaks backward from the future, not a drop. And the resulting picture is memorable, a staircase. The first word can only see itself, the second sees 2 words, the 10th sees 10. Every position gets the largest context it's legally entitled to, and every position is trained at the same time in the same forward pass. This is called causal masking, or masked self-attention, and it is the quiet trick that turns attention into a machine that can write. And with that, every essential piece is on the table. Let's step back and look at the argument the paper actually made. Chapter 17, The Comparison That Won the Argument. Section 4 of the paper is a single table, and it is, I'd argue, the most persuasive page in it. The authors compare self-attention against recurrence and convolution on 3 specific measures. Measure 1, computational cost per layer. Self-attention costs on the order of n squared times d, where n is the sequence length and d the dimension. Recurrence costs n times d squared, and here they make a sharp practical point. In real models, d is 512 or more, while a typical sentence n is a few dozen words. When n is smaller than d, n squared times d is actually the cheaper of the two. Self-attention wasn't just more powerful. At sentence scale, it was less work. Measure 2, sequential operations. How many steps must happen strictly one after another before the layer is done? For recurrence, that's n, 1 per word, and you cannot parallelize it away. For self-attention, it's a constant, 1, regardless of sentence length. This is the number that graphics hardware cares about, and the gap here isn't an improvement, it's a different category of thing. Measure 3, and this is my favorite, maximum path length. How many steps must a signal travel to get from any word to any other word? In a recurrent network, up to n steps, and every step is a chance to degrade. In self-attention, 1, always 1, word 1 to word 500, a single hop. The paper argues directly that shorter paths make it easier to learn long-range dependencies, and that framing is the clearest justification in the whole document. Now, honesty about the cost, because that n squared has a sting in it. Self-attention is quadratic in sequence length. A sentence of 50 words means 2,500 pairs. A document of 10,000 tokens means 100 million. Double the length and you quadruple both the compute and the memory. The paper's own table admits it and even mentions restricted attention as a possible remedy. That single term, n squared, went on to define the next decade of research. Direct connections, total parallelism, and a real price to pay for both. That's the trade the field took, and it took it gladly. Chapter 18, where attention sits in the actual model. Attention is not the whole transformer. It's the most important part, but it lives inside a repeating unit, and the rest of that unit matters more than you'd guess. Each block has two halves. First, multi-head attention, where every word gathers information from every other word. Then, a small feed-forward network applied to each word independently. Two linear layers with a nonlinearity between them, expanding from 512 dimensions out to 2048 and back down. If attention is the words talking to each other, the feed-forward layer is each word going away and thinking about what it just heard on its own. Communication, then computation, alternating all the way up. And wrapped around both halves are two pieces of engineering that look boring and are absolutely essential. A residual connection, which adds each sublayer's input to its output, so information and gradients have a clean straight path all the way through the stack. And layer normalization, which keeps the scale of the numbers stable. Without these, a deep stack simply will not train. Every serious deep network built since has some version of them. Then you stack the block. The base model in the paper uses 6 of them in the encoder and 6 in the decoder. Modern large language models use far more, tends to over 100, and the stacking is where the real depth of understanding comes from. Early layers resolve local, surface things, roughly which word attaches to which. Later layers work with representations already rich with context and attend over meaning rather than words. Each layer's attention is looking at the output of the last one, so the notion of a word gets progressively more abstract as you climb. That's the complete picture. Now let's answer the question the title asked. Chapter 19, why attention was in fact all you need. We've built the entire mechanism. So let's take the paper's bold title seriously and ask why removing everything else turned out to be the right call. 3 reasons, and we've earned all of them. 1. Direct connections. Any two words one step apart, no decay across distance. 2. Total parallelism. No sequential dependency inside a layer, so the hardware runs flat out and training time collapses. 3, and this is the one nobody put in the title, it scales. Because it's essentially large matrix multiplications, you can make it bigger and bigger and bigger, and it keeps getting better. Recurrent models could not absorb scale like that. Attention could. And that 3rd reason is really the whole story of the last decade. The transformer turned out to be a shape you could pour almost unlimited data and compute into. Every large language model you have used is a stack of the blocks we just built, made enormous. The formula does not change. Only the size does. So here's everything in one breath. Every word produces a query, a key, and a value. Queries meet keys through dot products to score relevance. Scores are divided by the square root of dk, so softmax stays gentle. Softmax turns them into a budget that sums to 1. That budget blends the values into a new, context-aware version of each word. Run it in 8 parallel heads for 8 perspectives. Add positional encoding so order survives. Mask the future so the model can wrap it in residuals and a feed-forward layer, and stack it deep. That is attention, and that is the transformer. But this elegant mechanism was only the beginning. Remember that n squared. Over the years that followed, researchers pushed against it relentlessly, chasing longer memory, faster inference, and lower cost. Sparse attention, linear approximations, flash attention, group query attention, rotary positions, sliding windows, and challengers that question whether attention is all you need after all. That evolution from 2014 right up to today is the story of our next video. If watching Attention Finally Click was worth your time, give this one a like and subscribe because we are only getting deeper from here. We're building AI up from the ground, one blueprint at a time. I'll see you in the next one.